Okay, so we will be talking about fixed universe successors problem. This is also a problem to deal with the dynamic set. So, the goal is to maintain a dynamic set of set S of n element. So, at some point of time there are n elements in the set, and this set is coming from a fixed universe. So, a universe is fixed, we know the elements, who are the elements. So, this is a, so we have seen many dynamic set problems, like we have seen the heap. So, we have seen the binary balanced binary tree, balance BST. So, we have seen many dynamic set problem, but here problem is has a criteria that the elements are coming from the fixed universe. So, we know the elements where from they are coming, and the elements are coming from the universe U, which is basically 0, 1 to small u minus 1, and the size of the universe, say size of this universe is small u. Okay. So, this is the problem. So, S is a subset of U. So, the elements of S are coming from a fixed universe. So, we know the elements of S. So, this set is dynamic. So, our goal is to perform the operation like, so dynamic operation. So, what are the dynamic operation? It should perform the insert, delete, and also the successor and predecessor. So, this in the S set, so we should able to perform this operation, say insert. Insert means we should able to insert a x which is from the universe and which is not in S. So, this operation we should able to do. So, this is basically insert an element in S, insert an element from U in S. Okay. So, this is basically insert operation, and another dynamic operation is delete. So, we should able to delete a element from S. So, this is basically deleting an element x from S. Okay. So, these two operations is basically the dynamic operation, make this set dynamic. So, these two operations make this set dynamic. Okay. So, another operation is the successor query. So, we want to find a successor of S is coming from this. So, we want to find the successor, means next element after x in S. So, that is the successor query. So, this is basically find the next element in S, find the next element in S larger than x. Okay. So, x may be in S or may be from the universe. So, we have to find the next element of x in S. Okay. We will take an example, and similarly the another query is finding the predecessor. So, the previous element, find the previous element, find the previous element of x in S, find the previous element of x in S. Okay. So, these two query we must able to do, successor query and predecessor query. So, we need to have a data structure for this dynamic set S. Okay. So, we need to think of a data structure so that we can perform this operation in a efficient way. Okay. So, let us give an example. Suppose our universe is say 0 to 15. So, our u is 16. Okay. So, suppose small u is 16, that means our universe is 0, 1, 2 up to 15. So, our set is coming from this universe. We know the dynamic set element, dynamic set S, whose elements are coming from this. Now, suppose this we have a S, say for at some point of time S is say 1, 9, 10, 15. Suppose this is our S at some point of time. Okay. So, now if we what do we mean by successor? Suppose successor of say 2. So, successor of 2 is basically, so we want to find the next element of 2 in S. So, after 2 we have 9. So, successor of 2 is 9. Similarly, successor of 1, this is also 9. We want to find the next element of this x. X could be in X or may not be in S. So, but we have to find the next element after X, which is the next element in S. So, that is the successor query. Similarly, predecessor query. Okay. And so, we need to find a data structure. We need to think of a data structure for this dynamic set S, so that we can able to insert an element X, delete an element X, and this is fixed universe. That means universe is fixed. We know the elements are coming from this universe. The elements are coming from this set. So, S is always subset of U. So, that is called fixed universe successor problem. So, this is called fixed universe. Okay. So, now what type of data structure you can think for this problem? So, any suggestion for data structure like array? Okay. So, first suggestion is say array. So, suppose we maintain an array for S. So, we have S is basically we have say 1, 9, 10, 15. So, we maintain a array, I mean n dimensional array, I mean it could increase. So, it is a array. So, if it is a array, then how much time it will take to insert an element? So, this is not a sorted array, I mean we may not have a sorted array, just an unordered array. Unordered array, or we can make it sorted. Then problem is to insert, we have to again shift it. So, insert will take order of n time. Similarly, deletion will take order of n time. And if it is unordered array, then the successor query, successor of x will take also order of n time, because we just need to scan the array. I mean, we do not know whether it is greater than or not. So, maybe we can think for linked list. If it is linked list, let us think for linked list, unordered list. So, we have this S set. So, just maintain a linked list for this S set. So, 1, 9, 10, 15. So, again for unordered, if it is not sorted, if it is unordered, then insert will take, depending on how we will maintain the pointer, insert or delete. So, we have to search that element for delete. So, this all will take order of n, and even successor also, successor or predecessor will also take order of n, because we need to find the next element. This is another array, another linked list. So, we have to find the next element after this. Okay, so, this is the second option, linked list. Now, think about binary search tree, balanced binary search tree. So, if you maintain this in a balanced binary search tree, balanced BST, right, red black tree, balanced binary search tree. Okay. So, we stored this into the balanced binary search tree. So, 9, maybe 1, maybe 10, maybe 15, okay, like this. So, now the search will take, so insert will take log n time, because we have to just insert in a BST, and again we may need to make it balance. So, if you are using red black tree, it is just red black tree insert, deletion also same. So, and successor also, successor means so successor of, so this is a binary search tree. So, suppose we have few more elements, like say we have here, say we have 9, so we have say 7, and say we have 0 over here. Okay. Now, if we ask the which is the successor for this node, suppose successor of 7. So, for successor of 7, this is basically in order traversal, who is the next element after 7. So, it is basically we need to go like this. Okay, successor of 7 is 9. So, basically we need to go height of this tree. So, this successor will take basically order of log n, because this is a balanced tree. So, height will be log n. So, successor query will take, because for successor of 7 we need to go to the height of this tree. So, this is a order of log n. Okay. If size of n s is n. Okay, but now, but we want to have a data structure so that we can perform this successor query or insert or delete. We can perform this in order of log u. So, this is our target. So, we want to have a data structure for which we should able to find the successor, or we should able to insert in order of log u. So, how to get the time complexity log u? We have seen it is not log n, even log u. Yeah. So, how we can get a time complexity of a algorithm log n or log u? Any idea how we can get log? Suppose we have say log n elements and they are sorted, and now on this, suppose this is n, and on these elements we are doing the binary search. Then we can get this binary search will take order of log n. Okay. So, this binary search will take order of log n. Any recurrence can give us this solution, order of log u. Do you have any recurrence? Can you think of any recurrence which can give the solution order of log u? Like T of u equal to T of something plus order of 1. Can you suggest this so that we can get order of log u? Any recurrence will have this solution? Just think about it. So, if you put just root u, then we just replace root u by log u, then this is log u, then half will come out. So, this will give us the solution this will give us order of log u by master method. So, you can easily check this. So, this recurrence have the solution order of log u. So, somehow we need to achieve this recurrence in order to get the time complexity this. So, that is the goal, and this is the data structure which is invented by Peter van Emde Boas. So, the person is in 1997 this data structure was invented by Peter van Emde Boas. He solved this problem and he suggested a data structure which is basically give the successor query or the insertion in the time is order of log u. Okay. So, we have to get that data structure. So, we have to build that data structure. So, how we can build the data structure? So, we have seen that to get this we need to have this type of recurrence Tu is equal to so this recurrence of the solution order of log u. Just we put u is equal to log u, then by master method we get these solutions. Okay. So, let us start. So, for the starting point we need to think of a array data structure, simple array data structure. So, we have already seen an array data structure, but this array is for on S. So, can you think of, so this is the starting point. So, can you think of some other type of array for this problem? So, can you think of a array of, so we have universe of size u. So, can you think of an array of size u? So, this is called bit vector. So, what is a bit vector? So, we just maintain an array of u size. So, this is basically, so our u is 15. So, this is up to 15, 0 to 3 like this. Okay. Dot dot dot. Now, so how to insert? So, to insert we just, so if u of x is 1, if x in S 0, otherwise. So, just a bit vector, I mean switch on switch off, very nice data structure, 0 1 vector. Okay, like these are a room, if a person is there then we switch on the lights of the room, otherwise we switch off the light. So, if our S is say 1 9 10 15, then we have corresponding to these positions. So, this is 14, this is say dot dot dot, this is 9, this is say 10 dot dot dot, this is 14. So, we have 1 over here and 14 we have 1, 14 we don't 1 over here, and remaining are all zeros. So, this is the current position of this data structure u. So, this is a simple array, this is an array of, this is called bit vector, just a switch off switch on 0, very nice, very simple data structure, very effective. Okay. So, we just have a array of size n. So, u is a array of size, the capital U, this is the array of size. So, we start here array from 0 to 0, like in C language our array start from 0 to u minus 1. Okay. So, now if we use this data structure, so how to insert an element? So, suppose we want to insert say insert 3. So, what we do? We just go to u3 and we put, so insert 3 means we just go to u3, So, this is the U array U3 and we put it 1, switch on. So, we put it 1, very simple, and delete. Suppose we want to delete an element which is already there, suppose we want to delete say 9. Okay. So, how to delete it? So, we just go to that position 9 and we put it 0, switch off, the room is empty, nobody is there in that room, lights off. Okay. So, this is very simple data structure, but very powerful. So, this is the, so how much cost, and these two insert and deletion will take, both will take constant time. Just we are going to that corresponding that field and we put it 0 or 1 depending on we are deleting. Okay, now how to do the successor query? For successor query, how much time will it will take? Successor of, say successor of x. Okay. Now, suppose all the elements are 0 except the last one, and suppose we want to find the successor of 1, say, or maybe we have a 1 here. So, we have, suppose array position is this. So, 0, 1 and 15. So, for successor query, basically we need to scan whole array, and this array of size u. So, this will take worst case order of u, because we may need to scan the whole array. If the array is like this, suppose we are searching an element, our x is such that which is the, after this nobody is there except the end. Okay. So, that is the even if we search successor of say 2, this is also you have to scan whole elements after 2. So, that will take order of this. Okay. But we want to achieve by, this is not even log u. So, we want to achieve this by log u, but anyway this is a starting point, this is a good start. This is very simple data structure because deletion and insertion is very powerful, just a constant time, but only problem is with the successor. Okay. Now, how we can make it into root u, because our goal is to achieve this in log u. In order to get log u, we have to have the recurrence. This is our goal, log of log u. This is the goal we want to achieve. So, in order to get this, we need to somehow convert this into root u. So, how to convert this into root u? So, that is the question. So, we have a given array. So, how we can make it into square root of u? So, we have an element of u, we have an element of 16 over here, u is 16, for our this example u is 16, small u is 16. So, how we can make it into root u? I mean root u is 4. Any idea how to get a root u from this? So, that is the next step. So, how we can, given a array, how we can make it root u? Okay. So, this is step 2. So, to make it root u, what we can do? We can just take a square. I mean, if we have a 4 by 4 matrix, then it will give us 4 into 4, 16 element. So, we have to make a square, we have to make a square. So, what we do? We break, suppose this is our array of, so here array is 15. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, this is our u array. Okay. So, this is our u array, here u is, small u is 16. So, now we want to make it into square root of u. So, how we can do it? We want to break it into the blocks, so basically square. So, we want to make it into the blocks of 4. So, this is first block, this is called blocks or widget, or blocks. So, this is first block 1, 2, 3, 4, this is second block or second widget 1, 2, 3, 4, this is the next one 1, 2, 3, 4. So, just we will break it into the blocks. Then we have this first block 1, 2, 3, second block, third block and the fourth block like this. Okay. So, this way we have total u, this way we break it into. So, how many blocks are there? Square root of u, and what is the size of each block? Square root of u. So, this is the way we get the square root, I mean from u, we get square root from u. So, this then we will talk about how we will make the insertion and deletion in this data structure. This is the just the argumentation of this data structure. So, this is just a one dimensional array, this is two dimensional array. So, we will continue this in the next class. Thank you.